In this lesson, we are going to learn about an application of series to something called a power series. So here's the definition of a power series. You assume that x is a variable, then an infinite series of the form a sub n x to the n, which is given by this, is called a power series. It's kind of like in polynomial, except for polynomials have a finite number of terms. This is an infinite number of terms. And this one is centered at 0. And you can also center your power series around different points. This one is called a power series centered at c. So instead of it being x to a power, it's x minus c to a power. And what these power series will let us do is they're going to let us, say, approximate functions near a point. And how you think about these power series is that they are functions and their domain is the set of all x values such that the series will converge. So first, state where these following power series are centered. So notice this is just x to the n. This part is the a sub n part. So this is centered at c equal to 0. This one, the whole over n to the 5th, tells you the a sub n's are 1 over n to the 5. And the x minus 4 tells you that the center is at 4. So centered at c equals 4. And similarly here, this thing is center c equals -5. Now, a power series can be viewed as a function of x, where the domain of f is all x for which the power series converges. You have actually already seen power series in this class. I just gave them to you and didn't tell you what it was. You had something like this: n equals 0 to infinity, x minus 2 over 5 to the n. Notice how this is a power series centered at 2. It's the same thing as the sum from n equals 0 to infinity, x minus 2 to the n over 5 to the n. And you found that, say, like this thing, it was a geometric series, and it converged if the absolute value of x minus 2 over 5 was less than 1, which is the same thing as saying -1 is less than x minus 2 over 5, which is less than 1. Or -5 is less than x minus 2, which is less than 5, or -3 is less than x, which is less than 7. So this can be thought of as a function, and the domain of that function is all the numbers between -3 and 7. We're going to learn today how to handle more complicated things than just geometric series. So first, there is a theorem that states that if you have a power series, there are just 3 possibilities. The first is the series only converges when x equals c. Note that if x equals c, you get the sum from n equals 0 to infinity of a sub n times 0, which will just be a sum of a whole bunch of zeros, which will obviously converge to 0. Also, the possibility is that the series could converge for all x, or there is a positive number r such that the series converges if this absolute value is less than that number, and diverges if it is greater than their number. The number r in this third case is called the radius of convergence. In the first case, you see that the radius of convergence is equal to 0, since you only have one point of convergence. In the second case, since all x's converge, you see the radius is equal to infinity. Now, the interval of convergence is the interval that consists of all the values of x for which the series converges. So, for example, in this sum from n equals 0 to infinity, x minus 2 over 5 to the n, the interval of convergence would be -3 to 7. the radius of convergence, we got that the absolute value of x minus 2 had to be less than 5. That 5 is the radius of convergence. All right, here is an example where the series that we're looking at is not geometric. And so what we're going to use to attack these is the ratio test. So find the limit as n goes to infinity of a sub n plus 1 over a sub n. All right, inputting n plus 1, we have x minus 5 to the n plus first, all over n plus 1, multiplied by n over x minus 5 to the n. Now the x minus 5 to the n cancels, just leaving us x minus 5 times n over n plus 1. Now we know that n is positive, but there's no guarantee that the x is positive or that x minus 5 is positive. So that has to remain in absolute value bars. Oh, that times n over n plus 1. And so as n goes to infinity, this n over n plus 1 term goes to 1, and this expression limits to the absolute value of x minus 5. Now by the ratio test, we'll have convergence if the absolute value of this x minus 5 is less than 1. At that stage, where you have absolute value of something with an x less than 1, you can say, oh, my radius of convergence is 1. Now to find the interval of convergence, you expand this out into a compound inequality. You say, well, negative 1 has to be less than x minus 5, which is less than 1, or negative 4, positive 4, is less than x, which is less than 6. So your series converges for all the x's between 4 and 6. One reason this is called the radius of convergence is that it's like a one-dimensional circle. You have a point at 5, and you converge for the points 1 unit above and 1 unit below. Kind of think about how a circle's radius measures the distance from the center on both sides. That's why it's called the center of the interval and the radius of the interval. Okay, so you know that you converge between 4 and 6. Now the thing is that this ratio test is inconclusive when your ratio is equal to 1. So to completely find the interval of convergence, you have to test the endpoints. So you must actually test what happens when x equals 4 and what happens when x equals 6. So take x equals 4, plug it into your series, you get the sum from n equals 1 to infinity. Now 4 minus 5, that's negative 1 to the power of n over n. And these should most of the time be things you can tell quickly what happens to them. This is going to converge the limit test, the alternating series test. At x equals 6, we get the sum from n equals 1 to infinity. Well, 6 minus 5 is 1. 1 to the n is just 1 over n. That diverges. You can either say it's a p-series or you can say it's the harmonic series. And thus, the interval of convergence includes 4, square bracket, does not include 6. Or you could also write that as 4 is less than or equal to x, which is less than 6. Those are equivalent ways to say the same thing. Okay, let's try another one. Find the radius and interval of convergence for this guy. So let's apply actually in this case, let's apply the root test, because you have both the numerator and denominator raised to the nth power. So find the limit as n goes to infinity, nth root, absolute value of an. So that's the limit as n goes to infinity, absolute value x plus 2, because we don't know x is negative or not, all over 5. And holy moly, well, that's just going to be a constant, so that's just x plus 2 absolute valued over 5. So this will converge if this thing is less than 1, and that implies that the absolute value of x plus 2 is less than 5. Thus, r is equal to 5. And we also know that negative 5 must be less than x plus 2, which is less than 5, or negative 7 is less than x, which is less than 3. So that's our preliminary interval of convergence. Let's actually test the endpoints. So at x equals negative 7, we get the sum from n equals 0 to infinity, negative 5 to the n over 5 to the n, which is the same thing as negative 1 to the n. That diverges. Test for divergence. Because the terms don't go to 0, they oscillate between negative 1 and 1. At x equals 3, you get the sum from n equals 0 to infinity of 5 to the n over 5 to the n, which is the sum from n equals 0 to infinity of 1s, which also diverges. Test for divergence. And as a result, the interval of convergence does not include either endpoint. So the interval of convergence is either negative 7 to 3 with parentheses, or you can give it as negative 7 is less than x, which is less than 3. Okay. So far we've had examples where the radius of convergence actually is a whole number. Next, let's deal with some things, like what does it look like when you get a radius of convergence of 0 and a radius of convergence of infinity. So find radius of convergence of the series that is n factorial times x to the n. So let's apply the ratio test. an plus 1 over an. So when we input n plus 1, we have the limit as n goes to infinity. Well, that's going to be n plus 1 factorial x to the n plus 1 over n factorial x to the n. Well, that will be n plus 1 times the absolute value of x. And this is going to equal infinity unless x equals 0. If x equals 0, then 0 times n plus 1 will be 0, but, well, otherwise it's infinity. So that means that the interval of convergence is just 0, and the radius of convergence is also 0. So then your limit will only equal a finite number for a particular value of x, then the interval of convergence will just be one number. Okay, let's try another one of those. So find the interval and radius of convergence of this series. So let's do the limit as n goes to infinity, a ratio of the n plus first to the nth term. All right, first input n plus 1, negative 1 to the n plus 1, x to the 2 times n plus 1 over 2 to the 2 times n plus 1 times n plus 1 factorial squared multiplied by 2 to the 2n n factorial squared over negative 1 to the n x to the 2n. So that's the limit as n goes to infinity. absolute value x to the 2n times x squared, 2 to the 2n n factorial times n factorial, 2 to the 2n times 2 to the second. Now n plus 1 factorial is going to have n plus 1 times n factorial, another n plus 1 n factorial. You've got next to the 2n from over there. Holy moly. A whole bunch of stuff cancels. So the x to the 2n and the x to the 2n, the 2 to the 2n, the 2 to the 2n, n factorial, and are left with the limit as n goes to infinity of x squared over 4 times n plus 1 times n plus 1. And I could drop the absolute value bars there because x is squared and therefore always positive. Now notice that this limit is equal to 0 no matter what x is. X is always going to be a constant. How quickly this will go to 0 will depend on how large x is, but since x is a finite number, this will go to 0. And 0 is less than 1 always for any x. Thus, this series converges for any x. So the interval of convergence is minus infinity to infinity, and the radius of convergence is infinity. All right, let's try another one then. So find the limit as n goes to infinity. Notice we can't use the root test because this thing is not raised to an nth power. So negative 1 to the n plus 1, x minus 1 to the n plus 1, all over n plus 1 or n plus 2, times n plus 1 over negative 1 to the n, x minus 1 to the n. So that's the absolute value of x minus 1. Just thinking about what's going to cancel. The x minus 1 to the n's will cancel. The negative 1 to the n's don't matter, so just left with an x minus 1, n plus 1 over n plus 2. And so that will equal the absolute value of x minus 1, and will converge if this is less than 1. So thus, r is 1. Then to find the interval of convergence, we observe that negative 1 is less than x minus 1, which is less than 1, or 0 is less than x, which is less than 2. So we know that the x series will converge as long as x is between 0 and 2. We just have to figure out what happens at 0 and at 2. So at x equals 0, we have the sum from n equals 0 to infinity, negative 1 to the n, negative 1 to the n over n plus 1. Well, that looks a lot to me like it's going to be the sum from n equals 0 to infinity, 1 over n plus 1, which will diverge. Technically, to do it, you have to use the limit comparison test. But really, I think that just knowing that it diverges is totally enough. And at x equals 2, this 2 minus 1 to the n is just 1 to the n. We get the sum from n equals 0 to infinity, negative 1 to the n over n plus 1. And that will converge by the alternating series test. And so thus, your interval of convergence does not include 0, but does include 2. Okay, find the radius and interval of convergence for this guy. So the trickiest time with these series really is the factorials. So this one we'll go through in pretty extensive detail. So find the limit as n goes to infinity of the ratio of an plus 1 over an. So when you input n plus 1, we have 3x to the power of 3 times n plus 1 over 3 times n plus 1 plus 1. times 3n plus 1 factorial over x to the 3n plus 1. Now notice that what we really have here is x to the 3n plus 4, 3n plus 1 factorial over 3n plus 4 factorial times x to the 3n plus 1. Okay, so let's first expand everything out. So x to the 3n plus 4 is the same thing as x to the 3n x to the 4th. When you think about factorials, like say 5 factorial, that starts at 5 and counts down. 3n plus 4 factorial starts at 3n plus 4. 1 less is 3n plus 3. 1 less is 3n plus 2. From there, you're at 3n plus 1 on down, which is 3n plus 1 factorial. X to the 3n times x. Now you can see that this term, and this term are all left behind, while this 3n plus 1 factorial and that one cancel, the x to the 3n's cancel, and another one of the x's cancel. So you have the limit as n goes to infinity, absolute value of x cubed all over 3n plus 4 times 3n plus 3 times 3n plus 2. So no matter what x is, as n goes to infinity, you're going to have a number divided by something that's getting bigger and bigger and bigger. This limit is equal to 0, which is less than 1 always, no matter what x is. And thus this series converges for all x. Now what that means is that your interval of convergence, I'm going to use IOC for that, is minus infinity to infinity, and your radius of convergence is infinity. All right, one last example. Find the radius and interval of convergence of this series. Okay, so let's apply the ratio test. Notice that root n screws up the root test. Okay, limit n goes to infinity, so an plus 1, 2x minus 1 to the n plus 1, 5 to the n plus 1, root n plus 1, multiplied by 5 to the n root n over 2x minus 1 to the n. Okay, so that's going to give us just a 2x minus 1 and a root n in the numerator. And the denominator, we're going to have a 5 and a root n plus 1. So that's the same thing as the limit as n goes to infinity, absolute value 2x minus 1 over 5 times the big old root n over n plus 1. Well, the stuff inside the root sign, as n goes to infinity, that goes to 1. So this is the absolute value of 2x minus 1 over 5. For convergence, we need this to be less than 1. And that implies that the absolute value of 2x minus 1 is less than 5. Now here's the one tricky thing. Your radius of convergence is not 5. And the reason that that is the case is because you find the radius of convergence when the coefficient of this x is 1. The coefficient of x right now is 2. So how you can fix that is you can divide everybody by 2, make this into x minus a half is less than 5 halves. And then you can say, okay, r is equal to 5 halves or 2.5. So just be aware of that you find the radius of convergence when you have this expressed as x plus or minus a number. If it was 2x plus or minus a number, you have to sort of mess with that a little bit first. But don't worry, you'll get whole numbers back once you find the endpoints of the interval. So that purple inequality means that negative 5/2 is less than x minus a half, which is less than 5/2. Or adding 1/2, it means that negative 2 is less than x, which is less than 3. So notice that the total length of this interval is 5. The r is half of that length. The final thing we need to do here is test the endpoints. So at x equals negative 2, when you plug that in, you get the sum from n equals 1 to infinity. So negative 2 times 2 is negative 2, minus 1 is negative 5. So negative 5 to the n over 5 to the n root n. Well, the 5 to the n's cancel, leaving us a negative 1 to the n. And that will converge by the alternating series test. At x equals 3, it's pretty similar, except for that 3 plus 2. You do 3 times 2 is 6, and 6 minus 1 is now positive 5. So you have positive 5 to the n over 5 to the n root n, which is the sum from n equals 1 to infinity, 1 over root n, and that diverges. P is equal to 1/2, which is less than 1. And then you can tell me that your interval of convergence includes negative 2, but does not include 3. It is not the case that a series will always converge at one endpoint and diverge at the other. It's just a lot of the examples have sort of gone that way. It is definitely theoretically possible for a series to converge at both endpoints, or neither. Both cases are possible. So either left endpoint only, right endpoint only, both endpoints, or none. Those are all possibilities.